Ignition, the dawn of the mini-suns. For as long as humanity has gazed into the night sky, the stars have been symbols of wonder, mystery, and unreachable power. They shimmered with a light older than civilization itself, their energy born from forces so immense that for centuries, even the greatest minds could only dream of understanding them. That energy, fusion, was the process that powered the universe. And now, it was the process humanity was learning to master. Fusion energy, at its heart, is the same mechanism that allows our sun to shine. Deep in the sun's core, the pressure and temperature are so extreme that hydrogen atoms, normally repelling each other because of their positive charges, are forced together. When they merge, they form helium, releasing an enormous burst of energy. This reaction is described by Einstein's famous equation, E=mc², where a tiny amount of mass is converted directly into energy. In the heart of every star, this happens trillions of times every second, bathing space in radiant light and heat. Scientists have long sought to replicate that same reaction on Earth, a star in a bottle. The concept seems simple. Take isotopes of hydrogen, such as deuterium and tritium, heat them to over 100 million degrees, and let them fuse. But simple, in this case, is deceiving. The sun's gravity naturally confines its plasma, a seething, electrically charged superparticles, while on Earth, humanity has had to invent artificial ways to contain it. If the plasma touches the walls of any chamber, it instantly cools, snuffing out the reaction. Achieving the perfect balance, pressure, heat, and containment, is a challenge that has eluded scientists for more than half a century. For decades, there were two main contenders in the quest for controlled fusion. One used powerful magnetic fields to confine the plasma in a donut-shaped device called a tokamak, pioneered by Soviet physicists in the 1950s. The other used intense beams of light, lasers, to compress a tiny pellet of fuel until it ignited. This second approach, called inertial confinement fusion, was the path taken by the U.S. National Ignition Facility, NIF. Built at Lawrence Livermore National Laboratory, NIF's massive structure housed the most powerful laser system ever assembled, 192 beams converging in a single chamber to focus unimaginable energy onto a target smaller than a pea. For years, the goal was elusive. The energy used to power the lasers was always greater than the fusion energy released. The phrase break-even point, or ignition, became both a dream and a burden. Countless experiments ended in disappointment, each one teaching new lessons about symmetry, fuel quality, and precision timing. Yet, the scientists persisted. Because they knew, if humanity could ever achieve ignition, it would mark the beginning of a new era, an era of limitless, clean power. Then came December 5, 2022. A date that will be remembered like the first flight at Kitty Hawk, or the first step on the moon. Inside the target chamber of NIF, 192 laser beams fired simultaneously at a gold cylinder no larger than a pencil eraser. Inside that cylinder was a small capsule of frozen deuterium and tritium. In a fraction of a second, the lasers delivered over 2 megajoules of energy, compressing the fuel to conditions hotter than the center of the sun. And for the first time in human history, the reaction produced more energy than it consumed. Ignition had been achieved. In that moment, humanity lit its first mini-sun on Earth. The morning of December 5, 2022, began like countless others at Lawrence Livermore National Laboratory. The winter air was still, the hills of Northern California bathed in pale gold light. Inside the National Ignition Facility, A quiet hum filled the enormous structure. Engineers ran final calibrations, technicians checked diagnostics, and physicists gathered around monitors, their faces lit by the soft glow of data streams. No one said it aloud, but every person there knew, today could be the day. The team had prepared for this moment for years. Every variable had been refined to perfection. The tiny target capsule, smaller than a peppercorn, was made of diamond, engineered to nanometer precision. It contained a frozen mix of deuterium and tritium, isotopes of hydrogen harvested from seawater and lithium. The lasers, 192 in total, had been tuned to deliver an unprecedented pulse, 2.05 megajoules of energy in just a few billionths of a second. The alignment had to be flawless, even the slightest imperfection in symmetry could doom the reaction. At 1:03 a.m., the countdown began. The control room went silent except for the low murmur of machinery. Every monitor displayed the same numbers ticking down, the culmination of decades of failed attempts, refinements, and quiet determination. The project had once been ridiculed as a scientific impossibility, a billion-dollar science experiment that would never achieve ignition. But for the men and women at NIF, those criticisms had long since become background noise. Their eyes were fixed on the moment ahead. When the lasers fired, the world didn't shake. There was no thunder, no flash visible to the outside world. Instead, deep inside the target chamber, a sphere the size of a small house lined with polished metal, the 192 beams converged perfectly onto the capsule. In a fraction of a second, the outer layer of diamond vaporized, creating an inward force of unimaginable magnitude. The pressure exceeded 100 billion atmospheres. The temperature soared past 100 million degrees Celsius. Under those conditions, the hydrogen nuclei inside fused, forming helium, and releasing more than 3 megajoules of energy. For the first time in history, humanity had coaxed the universe's most powerful process into giving back more energy than it took. The number flashed across the screen, 3.15 mJ output. 2.05 mJ input. Ignition achieved. For a moment, no one spoke. Then the control room erupted into cheers, tears, and disbelief. Decades of work, once dismissed as futile, had finally crossed the threshold. Scientists embraced. Engineers stared at the data again and again, making sure it wasn't a dream. One researcher, overwhelmed, whispered, "We've done it. We made a star." The triumph wasn't just technical, it was emotional. Many of the researchers had dedicated their entire careers to this single goal. Some had started when NIF was still an empty foundation in the ground, others had taken over after mentors retired or passed away. It was the kind of project that spanned generations, a relay race of human perseverance. Within hours, word spread across the scientific world. The impossible had become possible. Energy researchers in Europe and Asia stopped their experiments to watch the live announcement. News outlets scrambled to verify what they were hearing. Ignition achieved was not just a scientific milestone, it was a phrase that carried the weight of human ambition itself. Like the first controlled flight or the splitting of the atom, it marked the dawn of a new era. But unlike those earlier revolutions, this one promised to heal, not harm, to power civilization without pollution, to end the age of fossil fuel dependence, to bring light without cost. Yet, even as celebration swept the lab, a quiet understanding lingered among the team: ignition was not the end. It was the beginning. Scaling a one-time experiment into a continuous, practical energy source would require decades of innovation, engineering, and willpower. The spark had been lit, but building the fire that could power humanity forever, that was a challenge for the next generation. Still, that night, for the first time, humanity had proof that it could harness the same process that fueled the stars. The power of creation itself now flickered, faint but real, in the hands of humankind. The story of humanity's pursuit of fusion energy is, in many ways, a story of faith, faith in science, in persistence, and in the idea that some problems are worth solving even if they take lifetimes. Decades before that historic moment at NIF in 2022, physicists and dreamers across the world had already dedicated their lives to the quest to capture the power of the stars. The journey began in the shadow of the atomic age. In the aftermath of World War II, the world had witnessed the devastating force of nuclear fission, the splitting of heavy atoms like uranium to release energy. It was powerful, but dangerous. Fission produced radioactive waste, carried the risk of meltdown, and left scars on the conscience of humanity. The scientists who had unlocked that destructive power began asking, could there be a cleaner way? One that didn't destroy, but illuminated? By the 1950s, research into nuclear fusion began in earnest. The concept was elegant: instead of splitting atoms apart, fuse like ones together. Hydrogen, the most abundant element in the universe, was the perfect candidate. Its isotopes, deuterium and tritium, were plentiful, found in seawater and lithium deposits. And when fused, they released enormous energy without long-lived radioactive waste. Fusion, in theory, was everything fission was not: safe, sustainable, and virtually limitless. But in practice, it was a nightmare of complexity. To fuse hydrogen atoms, one had to recreate the extreme conditions found in the heart of a star, temperatures exceeding 100 million degrees and pressures so high that matter entered a plasma state, where electrons and nuclei danced freely in a storm of charged particles. The problem wasn't producing that heat, it was containing it. In the Soviet Union, physicists Andrei Sakharov and Igor Tamm proposed an elegant solution: the tokamak. It used powerful magnetic fields to confine the plasma in a donut-shaped chamber, keeping it from touching the walls. Their invention became the foundation for most fusion research in the decades that followed. Western scientists, including those in the US and Europe, soon adopted the tokamak design, refining it into experimental machines like JET in the United Kingdom and ITER, a massive international collaboration being constructed in France. At the same time, others pursued a different path: inertial confinement fusion. Instead of magnets, it used lasers, so powerful and precise that they could compress a tiny fuel pellet in microseconds, mimicking the pressure of stellar cores. This was the approach chosen by the National Ignition Facility, founded in the 1990s as part of both scientific exploration and national security research. The laser-driven method was extraordinarily complex, involving near-perfect symmetry, nanometer precision, and extreme control over timing. For decades, it seemed that fusion was always 20 years away. Between 1950 and 2010, thousands of brilliant minds worked in near anonymity, chasing a dream that always seemed to slip beyond reach. Governments poured billions into the promise of clean energy. Newspapers occasionally reported on breakthroughs, but enthusiasm faded as progress remained painfully slow. Scientists joked grimly about the eternal 20 years, the ever-moving horizon of fusion's arrival. But behind the scenes, progress was being made. Diagnostics improved. laser technology advanced. Computational modeling became more accurate. And in the magnetic world, tokamaks reached new records of plasma temperature and confinement time. By the 2010s, private startups began to join the race, companies like Commonwealth Fusion Systems, Helion, and Tokamak Energy, bringing fresh funding and new ideas. For the first time, the quest for fusion wasn't just a government endeavor, it was a global movement. Then, as if fate itself was waiting, the pieces finally came together at NIF. It wasn't luck, it was the culmination of 70 years of scientific evolution, of ideas building on ideas, of failures becoming stepping stones. The success of the ignition shot in 2022 was not just a victory for Livermore, it was the triumph of humanity's collective determination. The physicists who had once scribbled equations on chalkboards in post-war laboratories had lit the path that led to that spark. Now, the dream was no longer theoretical. Humanity had seen fusion work, not in the heart of a distant star, but here, on Earth. The age of "what if" had ended. The age of "what's next" had begun. In the heart of the National Ignition Facility, the path to controlled fusion was not paved with fire, but with precision. Every success, every joule of energy released from hydrogen's core, depended on mastering the smallest details, microns, nanoseconds, and atoms. The ignition of December 5, 2022, was not magic, it was the result of the most complex symphony of physics ever conducted on Earth. At its core, the process was beautifully simple. Two atoms of hydrogen fused to become one atom of helium, releasing energy. But the act of forcing those atoms together required creating an environment as hot and dense as the Sun's interior, if only for a fleeting instant. The National Ignition Facility's approach, inertial confinement fusion, used light itself to create that environment. The setup began with a hole round, a hollow cylinder made of gold. The gold wasn't chosen for glamour but for its unique property of converting laser light into X-rays. Inside that cylinder sat the fuel capsule, a nearly perfect sphere smaller than a peppercorn. Its shell was made of ultra-smooth diamond, encasing a mixture of frozen deuterium and tritium, two heavy isotopes of hydrogen. Each capsule was a masterpiece of craftsmanship, with imperfections smaller than a human hair. When the experiment began, 192 laser beams, each traveling the length of a football field, fired simultaneously, their light split and amplified through a maze of mirrors, lenses, and frequency converters. The beams entered the hole round through tiny openings and struck its inner walls, generating an intense bath of X-rays that uniformly bombarded the capsule. In a fraction of a billionth of a second, the capsule's outer layer vaporized and exploded outward. According to Newton's third law, that outward explosion drove the inner layers inward, creating an immense, symmetrical implosion. The hydrogen fuel at the center was crushed to densities and pressures millions of times greater than those found at the core of Jupiter. Temperatures soared above 100 million degrees Celsius, 5 times hotter than the core of the Sun. At those conditions, something extraordinary happened. The deuterium and tritium nuclei, each positively charged and normally repelling each other, slammed together with enough force to overcome their natural repulsion. When they fused, they formed helium nuclei and released high-energy neutrons. Those neutrons escaped the fuel, carrying energy outward, while the helium stayed behind, heating the surrounding plasma and creating a self-sustaining burn. For a brief moment, a tiny sun was born on Earth. The key phrase, ignition, meant that the energy from fusion exceeded the energy delivered to the target. Specifically, 2.05 megajoules of laser energy produced 3.15 megajoules of fusion energy. Though still far less than the power consumed by the entire facility to charge the lasers, this was the holy grail of fusion physics, a reaction that could feed itself. For that instant, the laws of the cosmos bowed to human design. The afterglow of the shot told a deeper story. Sensors recorded a surge of neutron flux, proof that fusion had not only occurred but had spread through the fuel in a runaway cascade. The data matched predictions from decades of modeling. Every sensor, every diagnostic camera, confirmed the same truth: the barrier had been crossed. In the control room, the excitement was tempered with awe. Scientists understood that what they'd achieved was both monumental and minuscule. The reaction had lasted mere nanoseconds and occurred in a space no larger than a grain of sand. But the implications were infinite. If that reaction could be repeated continuously, scaled, and harnessed, it would mean an end to the world's energy problems. No more burning fossil fuels. No radioactive waste lasting millennia. Just pure, abundant power, drawn from the same force that lights the stars. In that moment, humanity wasn't just studying the universe. It was becoming part of it. The fusion fire had finally been tamed, if only for a heartbeat. When news of the ignition broke, it spread like solar flares across the planet. The announcement came quietly at first, just a press release from the U.S. Department of Energy, but within hours, the story dominated every headline. Ignition achieved. Two words that captured decades of human struggle, hope, and scientific wonder. Overnight, fusion transformed from science fiction to tangible reality. In laboratories and classrooms across the world, scientists who had devoted their lives to fusion research paused, stunned. Many had grown old chasing the dream, their careers marked by incremental progress and public indifference. Now, for the first time, their life's work had been vindicated. At the Princeton Plasma Physics Lab, an engineer in his 70s reportedly whispered, "We finally did it," though it wasn't his team who had fired the lasers. In the UK, Japan, Germany, and Korea, fusion researchers celebrated as if they had all been in that control room at Livermore, because, in truth, they were all part of the same journey. The political world reacted almost instantly. Energy ministers convened emergency meetings, not out of fear, but out of excitement. For decades, nations had been entangled in conflicts over oil, gas, and rare earth resources. Now, the prospect of virtually limitless clean energy had entered the realm of possibility. Governments pledged new funding for fusion research. The European Union expanded support for ITER in France. China accelerated development of its own magnetic confinement reactors. Private companies, once skeptical, began knocking on the doors of labs, eager to commercialize what they called the energy of the stars. Public reaction was a mixture of awe and disbelief. Headlines compared the achievement to the moon landing, the discovery of electricity, and the splitting of the atom, but this time, without the shadow of destruction. Environmental activists called it the end of the fossil age. Economists speculated on how fusion could reshape global markets, ending energy scarcity and reducing geopolitical tensions. Overnight, the phrase, "mini-suns on Earth," trended across social media, a poetic shorthand for humanity's newest triumph. But not everyone was convinced. Skeptics pointed out that the NIF experiment had produced net energy only within the capsule itself, not counting the enormous power required to run the lasers. It's like lighting a match with a flamethrower, one critic quipped. Still, others saw it differently. The first airplane didn't carry passengers, and the first light bulb barely lit a room, but both were beginnings. Fusion had crossed from theory into reality, and every technological revolution had begun with a moment just like this. In universities, enrollment in plasma physics and nuclear engineering soared. Documentaries and think pieces flooded the media. The young saw in fusion not just a scientific marvel, but a symbol of hope, proof that humanity could solve its biggest challenges through intellect and perseverance. Students began to call this new age, the Age of Light. Meanwhile, investors and startups poured into the field. Companies like Commonwealth Fusion Systems, Helion, and Tokamak Energy saw record funding. AI-powered modeling accelerated reactor design, and 3D printing enabled rapid prototyping of new materials that could withstand plasma temperatures. In the background, governments began discussing what a fusion-powered grid might look like, and how to transition from fossil fuels without collapsing economies built on them. And somewhere, in a quiet corner of the Livermore lab, the original NIF team gathered once more around the now famous target chamber. The silver sphere stood still, reflecting their faces in its mirrored surface. They had spent decades chasing an idea that most of the world had written off as fantasy, and now, every government, every company, every child who looked up at the stars would know what they had done. They had given humanity a glimpse of forever. But amid the celebration, the scientists knew what the headlines did not: achieving ignition once was not enough. To power the world, they would need to sustain it, to repeat it, refine it, and control it safely, continuously, efficiently. The road ahead was long, and fusion still had 1,000 mysteries to solve. The spark had been lit. Now humanity had to learn how to keep the fire alive. The first ignition was a spark, beautiful, fleeting, and fragile. But to power a city, a nation, or the entire world, humanity would need to learn how to hold that spark, to make it steady, controlled, and endless. The challenge was no longer to prove fusion could happen, but to make it happen again and again, efficiently and safely. The journey from that one perfect shot to a continuous power source would become the defining engineering quest of the 21st century. After December 2022, laboratories around the world entered a new kind of race. For the first time, the problem was no longer scientific doubt, it was engineering scale. The ignition shot at NIF had lasted only a few billionths of a second and produced energy too small to light a household bulb. The lasers required months to cool and reset for another attempt. To power the world, humanity would need a system that could fire 10 times per second, not once per month. Physicists began redesigning the entire process. Some proposed replacing the massive laser arrays with compact, high-efficiency diode-pumped lasers, capable of firing repeatedly with far less energy loss. Others explored magnetic fusion alternatives, building on decades of work from Tokamak reactors. The Tokamak approach, while different, had its own momentum. Machines like JET in the UK and East in China had already sustained plasma for minutes at a time. Now, private companies began merging these approaches, combining magnetic confinement with laser compression in hybrid reactors. The new frontier was materials science. No known metal could withstand the neutron bombardment of a sustained fusion reaction. Each neutron carried enough energy to displace atoms from the reactor walls, weakening the structure over time. Scientists began developing liquid metal walls, self-healing materials, and advanced composites that could absorb the blast while transferring heat to turbines. Behind the scenes, supercomputers modeled every reaction, predicting failures before they happened. Artificial intelligence became an essential partner in the fusion revolution, designing reactor geometries, optimizing magnetic fields, and even running control systems capable of reacting faster than any human could. Economists and engineers begin to speak in new terms: Q-plasma, Q-facility, Q-grid, measures of how much energy could be extracted versus how much was put in. The NIF shot had achieved Q equals 1.5, the first time fusion had ever surpassed break-even within the target. But to power a fusion plant, scientists estimated they would need Q greater than or equal to 10, meaning 10 times more energy out than in. Achieving that ratio would take decades of innovation, but optimism had returned. For the first time in human history, the laws of physics were no longer the problem. Around the world, governments began laying plans for demonstration plants. The US announced IgnitionNet, a network of public-private projects to build prototype reactors by the 2040s. In Europe, ITER aimed to begin plasma tests before the end of the decade, while the UK's STEP project planned its first grid-connected fusion plant by 2045. Private firms began setting even bolder goals, promising electricity from fusion within 15 years. Whether or not they would meet those deadlines, one thing was clear: the fusion age had begun. Yet amid the excitement, sober voices urged caution. Energy experts warned that transitioning to fusion too quickly could destabilize global economies built around fossil fuels. Oil-rich nations feared irrelevance, others saw opportunity. The politics of power, once defined by geography, were shifting toward technology. For the first time in history, energy could be everywhere and belong to everyone. Philosophers and theologians weighed in, too. Some saw in fusion the ultimate expression of humanity's divine spark, the moment when humankind learned not just to harness fire, but to create it. Others feared the consequences of such power. "We are building our own suns," one ethicist wrote. "The question is not whether we can, but whether we will remember what light is for." In the laboratories of Livermore, a new generation of scientists began their work. They stood beneath the same silver sphere where the first ignition had taken place, surrounded by instruments that had captured the brief birth of a star. For them, the event of 2022 wasn't a victory to rest upon, it was a responsibility to carry forward. The sun had shared its secret. Now humanity had to prove itself worthy of it. The dawn of fusion power marks the beginning of one of humanity's most profound eras, the Age of Light. The first ignition was not the end of discovery but the start of an unfolding story that will define centuries to come. As the 20th century belonged to oil and electricity, the 21st, and beyond, will belong to the stars. In the short term, the next 2 decades will be an age of transformation and trial. The early 2030s will see the rise of experimental reactors, compact, efficient, and modular, operating for minutes, then hours, then days at a time. Startups will partner with governments to test grid-connected systems, using fusion to supplement renewable sources like wind and solar. The technology will first appear not in cities, but in remote areas where fossil fuel transport is costly, research stations, islands, and data centers. By the 2040s, humanity may see its first continuous fusion plant feeding clean electricity directly into a national grid. But this revolution will not be easy. The engineering challenges are immense. Reactors must handle constant bombardment from high-energy neutrons. New materials, metals that heal themselves, ceramics that won't shatter under stress, superconductors that can operate at extreme magnetic fields, must be invented, not just improved. The economics, too, must shift. Energy from fusion must be cheaper than that from fossil fuels, or nations will hesitate to invest. And even as fusion becomes viable, societies will face hard questions about equity: who owns this power, who profits from it, and who is left behind. Still, the promise is extraordinary. Imagine cities powered by miniature suns, producing no greenhouse gases, leaving behind only helium and light. Imagine deserts blooming with electricity-fed agriculture, oceans desalinated by clean power, industries running without smoke or ash. The possibilities stretch as far as imagination allows: deep space colonies fueled by portable fusion cores, floating platforms generating energy for entire nations, interstellar missions sustained by fusion drives that burn hydrogen drawn from the void itself. Yet, like all great advances, fusion carries its shadows. The dangers are not in catastrophic explosions. Fusion reactions cannot run away like fission, but in human nature itself. Unlimited energy could lead to unchecked consumption, the exhaustion of other planetary resources, or even new forms of inequality between nations that harness fusion and those that cannot. A civilization without scarcity might face new ethical dilemmas: how to live responsibly when power is no longer the limiting factor. There are geopolitical dangers, too. Though fusion itself is clean, the path to it requires materials and technologies that overlap with weapons research. The same lasers that ignite fusion pellets can also simulate nuclear detonations. Balancing scientific progress with global safety will demand transparency, cooperation, and humility on a level humanity has rarely achieved. As for when the next great breakthrough will come, most experts believe we stand on the edge of it. The 2022 ignition was proof of concept. The 2030s will likely bring the first self-sustaining, repeating reactions at laboratory scale. By the 2040s, prototype power plants may emerge. And by the latter half of the century, fusion could become the backbone of the world's energy grid. The transition may take a lifetime, but the trajectory is now irreversible. The spark cannot be unlit. Long into the future, perhaps centuries from now, historians may look back at December 5, 2022, the way we look at the first flight or the discovery of fire, not as the moment everything was accomplished, but as the moment everything began. For in mastering fusion, humanity did something greater than creating energy. It proved that it could rise above its limits, that it could turn knowledge into light. The stars no longer burn alone. Humanity has joined them. And now, the future glows with the fire we have learned to call our own. The end.